here we go. So, we'll talk about parallel lines first. Okay, so we already know what parallel lines are, right? Okay, so parallel lines. The symbol for parallel lines in geometry is that. That's the symbol. Okay, that's the symbol. So, for example, if I were to draw a picture, I'm going to define it here. But if I were to draw a picture, okay, like so, and like so, okay, and I call this line L and this line M. Okay, I'm kind of using the cursive there. When when you see the single letter name for a line, it's typically the letter name is in cursive. It's typically a cursive, or at least lowercase, if not in cursive. Okay, do you guys still learn cursive, by the way? No. So you have no idea what cursive is.
I know cursive.
Oh, okay, so you elementary school. Oh, so you did learn it in elementary school. Oh, okay. Yeah. So you'll learn, Stephanie, that like your teachers sometimes tell you stories to then just make you do what they want you to do. I would never do that to you guys. I would never lie to you. Never lie. No, but yeah, cursive is one of those things where like kids realize like, why do we have to learn this? And the teachers are like, I don't know, but I'm paid to do it, so we have to do it. And then you like torture yourselves through it, and then you're like, wait till you get to middle school. That's all you're gonna do is write in cursive, and then you never really do because the teachers don't make you do it. And anyway, so yeah, okay. Sorry about that, but I'm going to write in cursive here, so that's a cursive L, in case you forgot, and that's a cursive M, okay, lowercase m. And so then we could, symbolically say that those two lines are parallel by putting that. That means L is parallel to M, or line L is parallel to M, okay. Line M, I guess I should say. Okay. Also, though, we can symbolically show two lines being parallel by putting little arrows. And sometimes those arrows are kind of blacked in, like that. Okay, but that also indicates that those two things are parallel. These little arrows. These are the marks for parallel. And I'm just going to use the symbol for parallel because I am lazy and I don't want to write it right now. Okay, so there you go. Marks for parallel. All right, so what are parallel lines? Well, they are coplanar. Coplanar lines, right? That means they're in the same plane, and they do not intersect. Okay, coplanar and do not intersect. All right. So there's that, right? All right. So then in coordinate geometry, okay, like on the coordinate plane, right, in coordinate geometry, okay, parallel lines have blank slope. And what goes in the blank? The same or equal. And it kind of makes sense, right? Because slope kind of determines, the way a line kind of goes, right? And so if you want both lines to kind of go in the same direction or go the same way, they need to have the same slope, right? If one line goes up 3, right 5, the other line had better go up 3, right 5, or eventually they will intersect. Okay. So the main way that we're going to be talking about lines is very much the main way you guys talked about lines in Algebra 1, okay, and I believe that was the slope-intercept form, right? So just as a quick refresher, slope-intercept form here, I guess I don't know, I'll say like, remember, I guess I'll say here, okay, y equals mx plus b, right? That's one of the ways to write the equation of a line, right? Write a linear equation. Did you guys talk about point-slope form at all in Common Core algebra? Point-slope form? So that's another form, that's another way to write the equation of a line. It actually becomes very useful in calculus, so, should you decide to continue your math career up to calculus, then your calculus teacher will probably encourage you to learn an additional form for writing the equation of a line. It's just a lot easier to write, it's easier and quicker to do what you want to do than writing in slope-intercept form. But we're in geometry, and slope-intercept form is the best way for us to go. Okay, M, right, represents the slope, right? B is the y-intercept. It's probably been drilled into your brains, but maybe not, though. Who knows? Okay. All right, so that's the important information. That's why we call it slope-intercept form, right? It's called slope-intercept form because when you have a line written in this form, you have the slope of the line, you have the y-intercept for your line. So let's take a look at an example here, then. And let's see. Let's say that we have line 1 is the equation y equals 3x plus 5, and line 2 is the equation y equals 3x minus 3. Okay. So, is line 1 parallel to line 2? So line 1 has the equation y equals 3x plus 5. Line 2 has the equation y equals 3x minus 3. So is line 1 parallel to line 2? What do we say? Mary, yes? Yes! How do you know?
Because they have the same slope.
Exactly right. What are their slopes?
3x.
Yeah, so 3. Exactly right. Or as a fraction, 3 over 1, right? So that's exactly right. That's the slope. Okay, so yes. Okay. The lines have the same slope. Now, what if I change this a little bit, and what if they had the same slope and the same y-intercept? Would they be parallel? Why not? They got the same slope. It'd be the same line, right? And if the two equations are graphing the same line, they're not really parallel, right? Because when we think parallel, we think they never really intersect. And when two lines completely overlap, they intersect everywhere, right? They intersect at every point. So we call those lines coincident, I think. So that's not that important, though. But anyway, yeah. So good, right? You need different y-intercepts, but the same slope to have parallel lines. All right. Perpendicular. Perpendicular. Okay. Perpendicular lines have blank slopes. Alright, so how do you determine if two lines are perpendicular? What's true about their slopes? Can't be equal. If they're equal, that means they're parallel. So it's got to be something else. So what is it, Patrick? Yeah, they're opposite, and there's something else you have to do too. It's not just opposite, there's something else. So for example, if you have a slope of positive 2, then a negative 2 slope is not going to be, is not enough to say it's perpendicular.
Two slopes swap the numerator and the denominator.
There you go. Opposite reciprocal, that's the mathematical term for it, but
I'll leave my agenda in folder here.
you can check. I mean, I didn't see it. Is there anything in the desk there, Keegan?
No, I had it like back there.
Oh, you want to go check back there then?
Yeah.
Oh, okay. All right, so opposite reciprocal. No, it's not there.
No, it's not here.
I'm sorry, Kyle.
It's okay.
We'll see you Tuesday. All right, so opposite, right, just means to change the signs. All right, and the reciprocal means to flip the fraction. Right, that's what that means. Okay. Oh, and by the way, the symbol for perpendicular, perpendicular also has a symbol that looks like that. Okay, it's like an upside down capital T. Okay. An upside down capital T. And again, you use it in the same way. So for example, if I put like a little a cursive M and a cursive L and a cursive M there, and then I maybe draw like a little picture. So here's like line L, and here's like line M. Okay, and they're supposed to be perpendicular, but I don't know if I did a very good job drawing it that way. But there you go. You got an idea, right? There it is. All right, so let's do a quick example here. So, for example, a line y equals negative 2/3 x plus 5 would be perpendicular to a line with slope of, and then blank. So this line has the equation y equals negative 2/3 x plus 5. And if we were to then come up with a line perpendicular to it, what would the slope of that perpendicular line have to be? What would the slope of the line perpendicular to that have to be? So, 100. Yeah, positive, right? Positive 3/2. So the slope from this line, Hunter, was what? Negative 2/3, right? There's our slope. To get a perpendicular slope, you have to do the opposite, so positive, reciprocal, not 2/3, but 3/2. Okay, so negative becomes positive, 2/3 becomes 3/2, that's your perpendicular slope. Okay, and so this, any line with this slope will be perpendicular to that equation right there. Okay. All right, so here's one for you all to try. All right, so the question is parallel, perpendicular, or neither. Okay, that's like the question here. It's going to be one of those three. Okay, I want you guys to give this one a shot and see what you come up with. All right, line 1 has equation 3x plus y equals 1. And line 2 has equation x minus 3y equals negative 1. Okay, so go ahead and decide whether those two lines are parallel, whether they're perpendicular, or whether neither. They're neither parallel. I'm sure about where to go. I'll come around. You know, you put your hand up too, that'll be helpful. So, you think you have an answer, Michael? All right, we'll see. We'll see. How did you know that?
Because even though you switched the 1 to negative 1 and the y to negative y, you didn't switch the x to negative.
Okay. So without actually finding the slopes, you think you can tell just by looking at it, kind of thing? That is possible. It's possible. Okay. How do you know? What's the slope of this one? Is it in slope-intercept form? So you can't just look at it and kind of slope. I mean, some people might be able to just look at it after they do the kind of math in their head, but I mean, it's not in slope-intercept form. So you already got close. We'll see.
Sorry. So I'll say this. Looking at those two lines, well, first of all, how have we been determining whether things are parallel, perpendicular, or neither? What are we looking at? We want to know their, do you know their slopes by looking at those lines like that? Are those in slope-intercept form? Like that's slope-intercept form, right? So, are those in slope-intercept form? So if you can get them in slope-intercept form, then you can know some more information. Good answer there. Okay. Rather.
Okay. You can just tell. That's pretty impressive. I would have to work it out.
Well, I mean, yeah, so what's the number in front of the x? Negative 1, right? So negative 1 divided by negative 3. That's slope. That'll also be 1 over 2. Huh? Yeah, we can do the other one now, okay? Well, you gotta subtract over the x, yeah. Alright. One more minute here, and then we'll come back together. Bless you. Alright, we'll see. Change your mind. Alright, we'll see.
Okay. So let's take a look. All right, that wasn't a minute, but okay. So, parallel, perpendicular, or neither. Well, right now, we can't really tell, right? Because these are not in slope-intercept form. In fact, these are in standard form, when you have the x's and y's all over on one side. Not really helpful to kind of like be able to pull any information from those lines. We don't know. We can't really, like the slope of this line is not 3, okay? It's the number for the x, Mr. Whitmire. Right? Yeah, it's true, but is this in slope-intercept form? No. So the number in front of the x there is not necessarily the slope. You have to solve for y, right? Put it in slope-intercept form, and then you can determine what the slope is. So let's do that real quick here. So if I subtract 3x from both sides, I get y equals 1 minus 3x, or if you like, we could make it y equals negative 3x plus 1. Okay. Here, okay, we can, sorry, I got popped there. And then here for this one, let's see, we got to subtract x from both sides. We get negative 3y equals negative x minus 1. Okay, so subtract x from both sides, we get the negative x over here. And then divide through by negative 3. And let's see here, that's going to be y equals 1/3 fractions plus 1/3. Okay, so now we can see that the slope of our top line here is negative 3, or negative 3 over 1. The slope of our bottom line is 1 over 3, positive 1 over 3. So that means these two lines are perpendicular. You got it. Good job. Okay, opposite reciprocal slopes. All right, so there's that. Any questions there? Any questions there? So slope-intercept form, we got to put it in slope-intercept form so we can like read, you know, the information from the line that we need. Or you could graph them if you wanted to. That's another option as well. All right. So let's see here. Okay. So then, what do we call it when two lines intersect? All right, or they just intersect in kind of like a normal way. All right, so not in like a special like 90-degree angle kind of way. All right, and that is oblique. There is a word for it. So two lines are called oblique if they are coplanar and intersect at exactly one point. So, if lines are oblique, are they also then perpendicular? So no, right? Okay. If lines are perpendicular, are they always oblique? Yes, right? Because perpendicular lines are coplanar and they intersect at exactly one point. So basically, perpendicular lines are like a special case of oblique lines, right? Perpendicular lines are oblique lines that intersect and also form a right angle. Okay. Now there's one other, and I guess I'll draw a little picture there. Okay, there we go. Two lines intersecting at a single point. Okay. Can lines intersect at more than one point? Yeah, not in coordinate geometry, not in Cartesian plane coordinate geometry like that. There are other geometries where lines with like a different kind of like a definition for the line, they can intersect at more than one spot, but we won't worry about that. I'll say, like, if you think about, so there's a geometry, if you can just like picture this in your head, there's a geometry called sphere geometry, where you kind of like draw your geometry not in a two-dimensional plane, but on like the surface of a sphere, which you could like think about, which is like, how do I think about that? Well, think about the Earth, right? The Earth is just roughly a sphere, and so the lines in spherical geometry are circles that go around the sphere. Okay, and so for example, you can think of like the equator is like a line in spherical geometry, and so the equator is a line, and then you can think about like the prime meridian, right? That kind of like goes around like the top of the Earth, right, through the poles, through the North Pole and South Pole, and that intersects the equator at two places. So there you have two lines, the prime meridian, right, and like the equator, and they intersect at two places because of the way they define lines to be and stuff like that. But anyway, that's just kind of a little bit different thinking there. You won't have to worry about that unless you take some non-Euclidean geometry in college. And now you're all thinking, and I'll never do that because that just sounds terrible. So I understand. It was interesting, I thought. All right. One other thing we talk about are skew lines. Okay, skew lines are two lines that do not intersect and are not in the same plane. Ugh, can't write. Do not intersect and are not in the same plane. Okay, so I'm going to try and draw a picture here, three-dimensionally on two-dimensional paper. So do my best. Just use some perspective here, right? You guys in the engineering class have some practice with this already. Yeah, it's not bad. All right, and so then we got like here we could have like a line A. And then I could draw like line B like that. So line A will never intersect with line B. But we don't want to also say they're parallel, right? Because it doesn't really look like line A and line B are parallel. Parallel, we think, they're kind of like going in the same direction, and that's why they'll never intersect. But A and B are more like this, like my arm, one arm's going kind of up and down, one arm's kind of like going out in front of it, but they're never going to really intersect. So we don't want to call that parallel, so we call them skew. Skew can only really happen in three dimensions, right? So that's what we have there. Okay. And the last thing I want to talk about will be these some special angle pairs that happen when we have two lines crossed by a transversal. Okay, so that's skew. So any questions up to this point? Oblique, skew, parallel, perpendicular. We're all good there. All right. So the last little thing I want to do for us here is draw a little two lines crossed by a transversal. Okay. And I feel like, have we talked about transversals before? Forgive me, because I'm also teaching merit geometry, and I know I've talked with them about this, but have we talked about a transversal before? Okay, no, okay, so trans prefix means to go across, right? Like to transport something, okay, to take something from one place to another, right? So a transversal is a line that crosses other lines. So for example, let me just draw a little picture here. Okay, and this here is a transversal. Okay, this right here is a transversal. It's a line that intersects two other lines, two or more other lines. Okay, it's a transversal. By doing this, we kind of create a kind of a cluster of angles, right? So we have like one, I'm going to number these angles, 1, 2, 3, and 4. Okay, and then 5, 6, 7, and 8 down here. So we have like 8 angles that are created just by that one transversal crossing those two lines. Okay. And so, as a result, we create some relationships, okay? We have special names for some of these angle relationships. So the first kind of special angle relationship we have are called corresponding angles. Okay? So corresponding angles are angles that are kind of in the same position when you're looking from one cluster to another. So for example, one example of corresponding angles here are going to be angle 1 and angle 5. Okay, now how do I know that? Well, I'm looking here at angle 1. Angle 1 is kind of like in this cluster. It's kind of like the upper right part of that cluster. Likewise, angle 5 in this cluster is like the upper right. Okay? Someone want to raise their hand and tell me what's another pair of corresponding angles there? Yeah, Stephanie.
Angle 2 and angle 6.
There you go. Angle 2 and angle 6. Michael, you got another pair?
Angle 4 and 8.
Angle 4 and angle 8. Are there any more? Oh, yeah. Let me just zoom out some. And then, I see one more pair there. What is it?
Angle 3 and 7.
Angle 3 and angle 7. That's right, yeah. Okay. So those are called corresponding angles. They're in the same kind of position there. Okay. Then we also have alternate interior angles. Okay, alternate interior angles. So, when I say alternate, that means they are these angle pairs. One will be on the one side of the transversal, one will be on the other side of the transversal here. Okay, and then interior. Well, when I say interior, I mean like this space is the interior. Okay, so yeah.
4 and 6.
So exactly right, Tanner. 4 and 6 would be alternate interior. Are there any more? Audrey?
3 and 5.
Yep, 3 and 5. And are there any more than those? Anyone see any other alternate interior? Okay, and right. So I'll take your silence as a no, and that's correct. There are no more, okay? That's it. There's just those two pairs, all right? So we have alternate interior. Well, guess what? We also have alternate exterior. Okay. Okay, and so like this is the exterior right out here. It's not the interior, so it's not the space. I know, sorry, my hand is in the way. The exterior, it's not the space between those two lines. It's the space outside those two lines. Okay, so what would be an example of alternate exterior angles here? So Maria, what do you say?
Angle 2 and angle 7.
Angle 2 and angle 7. So 2 and 7 are not alternate. They are exterior, but they're not alternate exterior. So it would be 2 and... Yeah, it's angle 2 and angle 8. Yep, angle 2 and angle 8. Do you see that?
Yeah.
Okay. And then, Elizabeth, do you have another pair?
1 and 7.
There you go. Angle 1 and angle 7. Are there any more?
No.
Yeah, no, that's it. Just those two pairs. Okay. And I got one more pair here for us. Co-interior angles, also sometimes called same side interior. Okay, same side interior as well. angles. Okay? And so again, we're talking about just the angles in between those two lines. We're talking about the co-interior. Co means to share, so they share the same side. So yeah, so Tanner, what do you say? So 3 and 6, exactly right. And then, what's the other pair there? Anybody? Patrick?
Angle 4 and angle 5.
Yep, angle 4 and angle 5, exactly. Okay. Later, we'll look at relationships, or like why we bother even naming those. Okay, like what's special about them. Okay, but for right now, we'll just worry about just being able to identify them correctly. Okay. Now, don't forget there's other angles in here, right? Like for example, vertical angles are in here, right? For example, 6 and 8, 7 and 5, 3 and 1, 2 and 4. Those are all vertical. We also have linear pairs in here, right? 5 and 8, linear pairs. 6 and 5, linear pairs. 7 and 8, linear pairs. 6 and 7, or 1 and 2, 2 and 3, 3 and 4, 4 and 1. Okay, all those are linear pairs. Okay, so those are the other angle relationships that we still can apply here, right? Okay, so there's that. All right, we're going to stop there. I think that's all I wanted to show. So yeah, okay. So I'm going to get you guys your assignment, and you have a good 20 minutes to knock it out.